Alright. Let's do this. So, let's text this out on Remind. We are live. So, chemistry, and chemistry. Alright, so tonight we have a few things on the agenda. So, it's going to seem long. I think it'll be shorter than you think. A little bit of a different background here. That's okay. So, we got periodic table, excuse me, moles and molar mass, percent composition, and empirical versus molecular formula. So, I'm going to start with periodic table because I think that's pretty quick. So, first, let's go to the periodic table and let's try to figure out what the heck it shows us. What is on the periodic table? What is useful? How much pieces of information can you get from just looking at the periodic table? So, I did this the other day, but might as well color code it again because it is important. So, everything I'm highlighting in orange are your metals. So, orange equals metal. And I'm going to be erasing this a lot, I think, because I'm going to be writing on it so much. So, just keep that in mind. The staircase here, so B, Si, germanium, As, Sb, Te, Po. The green is going to equal your metalloids. And they're called metalloids because they have like properties of metals and nonmetals. They're semi-conductive. You know, they're not quite as like brittle as a nonmetal, but they're not going to have those malleable, ductile properties of a metal. So they're called metalloids because they're in the middle. And then what I'm going to highlight in blue, or yeah, why not? Blue. These are your nonmetals. So, blue are your nonmetals. And I covered that in one of the videos I did. I don't really remember which one. But, so the first thing is to always make sure you have a good idea on what's a metal and what's a nonmetal. Because there's questions as simple as that. Ionic bonding will be between metals and nonmetals. Molecular compounds will be between nonmetals only. So just make sure we have straight who's the metal, who's the nonmetal. I'm going to erase this part right here. Maybe I'll just move it up. So the orange, we said, orange, how do you pronounce that, Mr. G? Who cares? So, it is your metal. So let's look at the key. The key is unbelievably helpful. So we have atomic mass, and this is your weighted average atomic. Whoa. Let's make this a different size. This is your average atomic mass, because you'll notice it's a decimal. So this is an average atomic mass, and it's based on all the isotopes of that substance. So it's not just simply protons and neutrons combined. It is an average of all the isotopes of that given element. But as usual, the only two subatomic particles involved in atomic mass are protons and neutrons, not electrons. We have this symbol, which if we don't remember the name for that symbol, you can always look it up on table S, which will also have a wide variety of information. So we got the symbol. We have the atomic number, which is just your protons. We also have the electron configuration, which tells you the location of electrons. And that should be the same as the amount of protons, which as we see here, 4 plus 2 is 6. So as you go down the groups of your periodic table, you'll notice that the electron configuration gets greater and greater, and that corresponds to what shell or energy level these electrons are in, where the first shell is very close to the nucleus, and the second shell is a little further away, and they just keep getting further and further and further and further away. And the last thing are your oxidation states, which sometimes we'll call charges. And these are selected oxidation states. So some of these atoms can have oxidation states not seen here, but we got to keep something in mind that you'll only see these if something is given with that charge. So they say you have a fluorine ion, and you'll see it written like this. So this is an ion. Or these we start to use when they're in a chemical bond. So review my naming and formula writing video or my bonding video to see where these come into play. But the charge, whatever it is equal to, so your charge is based on how many electrons you have. So if you have a negative charge, that means you have more electrons than protons. So when you're trying to figure out how many electrons you have, if you're given a certain charge, and you know that protons minus your electrons should equal your charge, that means the protons minus the charge should give you how many electrons you have. So if you know you have a charge of -4, so let's say you were looking at this charge right here, -4, you know carbon has 6 protons. 6 minus a -4 will give you 10 electrons. So there's a lot of information you can just get from the numbers just given to you on the periodic table. A lot of information. All right, I'm going to do some erasing down here. So feel free to pause, fast forward, or rewind. But there's a lot more you get from just looking at this lovely, beautiful periodic table. So just to reiterate, we assume everything on this periodic table, when we look at it, unless you see a bond or it's noted in the problem, that these are all atoms, which means the charge is 0. The oxidation state is 0. So if you just see O2, we assume the charge is 0. But if you see H2O, and it's in a bond with something else that's not itself, we look at oxygen and we try to figure out what's oxygen's charge. Well, it's going to be -2. So just keep in mind the difference between an atom, which has no charge, and an ion, which has. All right, so it's always important to keep those two in mind. All right, so what else can we get from the periodic table? When you look at any given group, as you go down a group, these are most similar. All groups have similar properties. So any given group will have a bunch of elements in it. So let's take group 1, for example. We would say that Li, N, A, K, Rb, etc. all have similar chemical properties. And that's because, and you might be tempted to say charges are the same, but it's because their valence electrons are all the same. And if you're not sure, if you really don't remember, how do I justify that it's the valence electrons and not the charge? Well, just look at any other group. Let's take group 4. Titanium has a bunch of charges, but Ti has 2 valence electrons, Zr has 2 valence electrons, Hf has 2 valence electrons, etc. So any group, so the groups here are the ones going down, have similar chemical properties because they have the same amount of valence electrons. You can check any group and you'll see that that's true. So the groups are running up and down, and that's labeled here on the periodic table in multiple places. And their periods are going this way. So here are your periods. So your periods are going left to right. So your periods go, so period 1 is right here going that way. There's period 2, 3, 4, etc. All right, so those are groups and periods. Keep those straight. Okay, what else? As you go down a group, your electron shells increase by 1 each time. And I like to keep that in mind because when you get down to the bottom, they kind of run out of space, like right here. The first 2 energy levels, you don't see that 2-8. So they run out of space, so they don't include the 2-8 for francium and radium. But they're still there. So just keep in mind every time you go down a group, so let's take Be has 2 energy levels, 3, 4, 5, 6, 7 in radium. So every time you go down the group, the energy levels will increase by 1 each time. So that's something good to keep in mind on the periodic table. Your trends. There are a few periodic trends. So this thing is organized pretty well. It's mainly organized by atomic number. So the atomic number increases by 1 each step. It's also organized by things with similar properties. The metals are in one place, the non-metals are in another place. But there's also a fair amount of trends you can get by looking at the periodic table. So if you are going across the periodic table, if you go up a group and across, so your general trend is to go up this way, kind of make that triangle there. So I'll rewrite it down here. If you're going this way to there, so up a group, right across a period, or generally trend upwards like that, your electronegativity is increasing, your ionization energy is increasing, and your atomic radius is decreasing. The opposite is also true. If you're trending down a group or right to left across a period, I should write it the other way. So if you're trending this way, going down, aka down a group, and left to right across a period, it's the exact opposite of what you see on the right side. So your electronegativity goes down, your ionization energy goes down, and your atomic radius is going up. Now, Regents Day gets here. It's June 20th. You just took a bunch of Regents. Summer is literally staring at you through the doors of the gymnasium. What if you forget these trends? You can always look them up on Table S. So, let's say, for example, that a question is asking you to compare the electronegativities. It wants to know the general trend of electronegativities in period 4. Now, you can take the very, very long amount of time to look up K, Ca, Se, Ti, V, etc., etc. What are all their electronegativities? Or you can find K, find Br, and call it a day right there and see what the difference is. So for K, its electronegativity is 0.8. So I'm in the electronegativity row. And for Br, its electronegativity is 3. So I believe as you go down this way, generally speaking, from K to Br, electronegativity is going up. You can also look at ionization energy. Ionization energy for K and Br. Here's K. Here's Br. So generally speaking, as you're going across period 4, well, ionization energy is also going up. And you can also do atomic radius, the other trend. So here's K. Yeah. Here's K. Here's BR. And again, generally speaking, as you go across the period, it tends to trend down. So that confirms the trends. And you can also compare groups. Now, groups is going to be a little bit harder, but you can look them up. So let's say you're comparing group 16, which is oxygen's group. So you have oxygen, sulfur, selenium, etc., etc. So I'm just going to do one of them because you'll get the idea. You'll find O's electronegativity, 3.4. There's sulfurs at 2.6. There's selenium, also at 2.6. What was the next one? TE. Tellurium at 2.1. So this again confirms the trend. Generally speaking, even though two of them were the same, generally speaking, from top to bottom in a group, it's going down in electronegativity. And you'll notice the same trend in ionization energy as you go down a group, etc., etc. So, if you forget the trends, you forgot to memorize them, you're panicking, you think you're going to get this wrong, you're not going to get this wrong. Use table S to your advantage. So, pick the two elements in a given group. If they're asking you to compare a group, just pick oxygen and something below it, like TE, something far below it, and compare those. Or if they're asking you to compare them in a period, again, pick the first one and pick the last one. Ignore the noble gases, ignore group 18, and compare them using table S. Another great thing about table S to keep in mind, notice this word, properties of elements, not compounds. Every once in a while, again on test day, we get a little flustered, and there's a question about H2O's boiling point or whatever. And people like to go to table S and look up H's and O's and start combining them together. Don't do that. These are about elements only, not compounds. So, no compounds. If you ever get to a question that you're not quite sure where to go, double check table S. I've seen questions on years past where they want you to get the percent error for a density problem, and it gives you what you have calculated or what you have measured, and it's like talking about copper. And then it doesn't give you any other information about the density of copper. Well, it's on table S. So sometimes they won't tell you to go to table S, but if there's mentioning elements and their properties, which is what this table literally is, check it. It might help you out. Okay. Other things from the periodic table. Group names. I think they may or may not appear on the Regents. Some of these will sound familiar. But it's good to know. So group 1 are your alkali metals. So that's everything in group 1, starting at lithium, because hydrogen's not a metal. But it's still in group 1. Confusing, I know, but bear with me. Group 2 are your alkaline earth metals. Group 3 through 12 are your transition metals, because these are transitioning across the periodic table to your metalloids and then your nonmetals. Don't worry about 13, 14, 15, or 16. Again, your metalloids are right here on or underneath the staircase. Aluminum is not a metalloid. It is a metal. You get to group 17, which here will be your halogens. And then this one pops up very often. Group 18, which are your noble gases. All right, and let's talk about the noble gases for a sec. They like to ask about why, and again, if you need to pause this at any time, you can. I don't know if you can on a live stream, but you can pause it when you're watching this at a later date, because I do post all of these on my teacher site. I haven't posted last night's yet. It'll get up there. Be patient. Sometimes when these things are getting processed, the video comes out weird and gets really sped up. So I like to give it a full day or two before I put it on my website just to make sure it's okay. But when you're watching this for review purposes, feel free to pause it. There's a question they like to ask about noble gases, which is why are they stable? Why do they not react? What about them makes them not react? Why don't they form compounds? And it's because of the same reason of why they're all grouped in group 18. They all have 8 valence electrons. They have a stable octet in their valence shell. A lot of my students every once in a while will mention something about the charge. Well, if they have charges of 0, they can't bond, which is, great for neon. That's a true observation for neon. But if I look at xenon, I see some charges there for reasons that are not important for the regents. But, yeah, anyway. So, I think, let me make sure I didn't miss anything. I got to define some of these terms, but let me double check. Let me check my outline here that I did not miss anything. I don't think I did. You want to always double check. You don't want to make sure you're doing too much off the top of your head. A lot of it is periodic table just pops up in so many units anyway that a lot of it is like, didn't we talk about this already? And yeah, you're right. That would be a good observation. We did. Okay. Yeah, anything else I don't need the periodic table for. So, bye periodic table. It's nice to know ya. We'll be seeing you again later. Okay, you need to know what all those trends definitions are, because they won't always say which element is most electronegative. Sometimes they'll say which element has the greatest attraction for electrons. So, electronegativity is the attraction for electrons. That looks like it says attract ion. Attraction for electrons. Ionization energy is all about the strength to remove electron. So these kind of go hand in hand. Non-metals like fluorine have a very high energy, very high ionization energy, which means it takes a lot of energy to remove that electron, which also means they have a high electronegativity because they do want to attract electrons more than give them away. So the opposite's true for your metals. Your metals have a very low ionization energy, so it's pretty easy to remove that outermost electron. So let me keep that in mind. Remove outermost, aka remove your valence electrons. And since it's so easy, comparatively, to remove that outer electron from a metal, that also means they don't really have a high attraction for electrons. So they have a low electronegativity. Atomic radius is pretty straightforward. This is just all about your electron shells. So what's like the radius? If you go start at your nucleus and you go to your furthermost electron, how big is the atom? A question that pops up year to year to year is compare your ionic versus atomic. And I can say for certain that this popped up in 2017, June 2017, June 2014. It pops up pretty much on every June Regents, or at least one of the Regents in that year. So it's a popular question. And the answer depends on the atom you're talking about. So if you're talking about a metal, let's say, and I've seen this one so many times, potassium. So potassium as an atom versus potassium as a charged ion. So potassium as an atom is 2,8,8,1. Versus potassium as an ion, its charge is +1. Protons minus charge is electrons. So 19 protons in K minus the charge of 1 gives you 18 electrons. Versus over here, the 19 protons equals the 19 electrons. Because in an atom, the protons and the electrons are the same. So, since we have 18 electrons here, we've lost an electron. A positive charge means you have lost an electron. So this is now 288. This has 4 shells, or 4 energy levels. This has 3. So, generally speaking, for your metals / positive ions, you lose an electron, and usually that also means you lose an electron shell. And since you've lost that, the atomic radius is always bigger than the ionic radius. Now, for a negative ion, let's say you're doing fluorine. Fluorine as an atom is 2,7. And fluorine as an ion is charged -1. So fluorine usually has 9 protons, which equal the 9 electrons that you see, because 2 + 7 is 9. But if I do 9 minus a -1, I get 10 electrons. So negative means you gain electrons. So now I'm 2-8. And because of this other atomic structure effects, you can always talk about nuclear charge and shielding and stuff like that. Since this one, generally speaking, has gained an electron, it is bigger. Now, a lot of teachers, and this is perfectly fine, perfectly normal, will say, since this one has an extra electron and the amount of protons has remained the same, you might see this shielding effect going on, or you might see something about the electrons colliding more and more and more. And since there's more electrons than the protons, that attraction is not as strong. These are all great reasons, great things to talk about. But generally speaking, I feel comfortable with the fact that if you understand that this has gained an electron, as atoms gain electrons, they will start to get bigger. So for a non, which will often be your nonmetals, the ionic radius is bigger than your atomic radius. And that's about it. That's all I really wanted to talk about with periodic table. So, let's get into some math. Let's start with molar mass, also known as gram formula mass. So given a compound, you need to be able to tell me how much does it weigh based on the masses you find on the periodic table. So let's say you had H2SO4. First, when you read a formula, these little numbers go with the atom that is directly before it. So, sometimes it's easier to rewrite this as 2H, 1S, and 4 O's. So 2H, 1S, and 4 O's. How much does this compound weigh? What is its molar mass? What is its gram formula mass? Periodic table. Let's get the masses for all these things. Now I'm going to round a little bit just to make the math quicker and easier for me so I don't have to be sitting here doing calculator work. So hydrogen weighs about 1. Oxygen weighs about 16. And sulfur weighs about 32. So I have 2 hydrogens times a weight of 1 would give it a weight of 2. 1 sulfur times a weight of 32 will give it a weight of 32. And then 4 oxygens times a weight of 16 will give it a weight of 64. Sum these all together, add them up. So 64 and 32 is 96. 96 plus 2 is 98. So this gram formula mass is 98 grams per 1, because there's a 1 in front of here, an imaginary 1, but it's there, per 1 mole of this compound. Let's do one that has some parentheses. Let's say you had Mg, NO3, 2. So again, the small numbers correspond to what is directly before it. But this number 2 has a parentheses directly before it. So that 2 includes the nitrogens and the 3 oxygens. So you can think of this as your 1 Mg, your 2 nitrogens, and 2 times 3 is 6 oxygens. If you're having trouble realizing what I just did, expand this formula out. You have Mg and then 2 NO3s, because that 2 is applying to the entire NO3 in parentheses. So if I add these all up, I see 1 Mg, I see 2 Ns, and I see 3 plus 3, 6 oxygens. So, again, pause it right there if you need to. Let's look up their masses. You're going to go to the periodic table. Your 1 Mg weighs 24. Your 2 nitrogens weigh about 14. And your 6 oxygens weigh about 16. So we have 24 plus 28 plus 96. Yeah. So add those all up. 24 and 28 is 52. 52 and 96, 48 grams per mole. I'm just checking the math in my head again. That looks good. All right. I'm not going to do chemical reactions today. All right, let's do moles. So there's a formula for moles on your reference table that you can use if you want, where the number of moles, I wanted to highlight, is the given mass, aka what did they give you in the problem? And if they didn't give you a mass in the problem, you're solving for that. And the gram formula mass, which is exactly what we've just been doing, getting the compound and determining what is the total mass of all these individual atoms in my compound. So let's do a couple calculations involving moles. What if the question was, how many moles are in 30 grams of H2O? Good old water. So, how many moles are in 30 grams of H2O? Hey, that right here was given to you. That's your given mass. So moles equals 30 grams divided by the gram formula mass for water. So your 2 hydrogens plus your 1 oxygen will give you 18. Divide those two numbers together and you should get like 1.7. 1.67 moles. So if you're asked to calculate moles when given a mass, so grams equals a unit for mass, you just take the mass that they gave you and you divide it by the mass of the compound, aka the gram formula mass. What if you're asked how many grams are in 0.25 moles of ammonia? Set up that equation again. 0.25 moles, because moles was given, equals, I wasn't given a mass because I'm solving for it. X, that's my given mass, over the gram formula mass of NH3, which is 14 plus 3, 17. Uh-oh, algebra. Put this over 1. And now it looks like a lovely proportion. So you just cross multiply. So 17 times 0.25, 17 divided by 4 should be a little less, slightly more than 4. Slightly more than 4. I'm going to go with 4.18. No, I was off. 4 1/4. So X equals 4.25 moles. Sorry, not moles. You were solving for grams. And that is how you do moles. So, it's about as complicated as it's going to get. Some of you, I'm sure, have seen like really complicated problems involving moles. No. So, that's about as complicated as you're going to get. If you've seen, these are good. Nothing wrong with your teacher introducing this to you. If you've used this number before, or this number before, no. They just won't appear. All right, percent comp. You have that as well. It's a generic formula, but it applies for any instance where you need to find the percent composition of whatever. And it's mass of part divided by the mass of whole. So what we're going to do tonight is just the percent composition of certain elements in certain compounds. So just to make my life a bit easier, I'm going to use the compounds we already did. Where the last one we did was MgNO3 and if memory serves me right, this weighed 148 grams per mole. Yes. Okay. So, what if the question was, what is the percent composition of oxygen in this formula? So, you need to do part over whole times 100. Don't forget that. If you don't multiply it by 100, it's not a percent. You're wrong. So, your whole is 148 grams. 148. You can do it. You have 2 times 3, 6 oxygens, times how much oxygen weighs, which is 16. So it's 96 over 148 times 100. And when you do that, you should get about 65%. And that should be to the correct sig fix. What was the first one I did? H2SO4, which we said weighed 98? Yeah. So, what is the percent comp of hydrogen in H2SO4? So, there's 2 hydrogens times a weight of 1 divided by 98, because that's how much H2SO4 weighs. We did that calculation before, so if you think I'm going a little fast, we did 98 before. So, there's 2 hydrogens. They each weigh 1, so I'm going to do 2 divided by 98, and then times 100. Don't forget the times 100. So if I do 2 divided by 98 times 100, I should get about 2%. 2%. And that's percent comp. We're going to do more percent comps when we do solutions, because we make some silly mistakes with solutions. Also, kids hate solutions. But, yeah. Last topic. Empirical versus molecular formula. So, let's do it at the basic level. Molecular formula is the actual formula, like the real formula. So if I say you have glucose, its molecular formula would be C6H12O6. Nothing else is glucose. That's glucose. Period. Don't tell me any other formula is glucose. Don't tell me any other formula for water is anything but H2O. So, when you look at this formula, that means for glucose here, for every 6 carbons, you will get 12 hydrogens and 6 oxygens. They're in a 6 to 12 to 6 ratio with each other. So you can keep multiplying these or by 2, 3, 4, all of them by the same number, and you will always get that same ratio. For every 6 carbons, there's 12 hydrogens and 6 oxygens. We can simplify this, though. So your empirical formula is simplified. It's your lowest ratios. So what does that mean? So if you have C6H12O6 as your molecular formula, those numbers, those subscripts, those tiny numbers, are divisible by 6. And if I divide each of them by 6, you get CH2O. And I'll put the 1s in there. You don't have to, but you can. So C1H2O1. I have simplified that to the lowest possible numbers I can. So it makes that ratio easier to understand. For every 1 carbon, I see 2 hydrogens and 1 oxygen. Let's do another one. Let's do N C6H14. Usually what I would say is if what you need to divide by isn't immediately obvious, like if you didn't pick the biggest number you could right away, if they're both even, just start with 2. I'm going to divide these each by 2. Get C, so this is the molecular. I'll get C3H7. Well, I can't divide that, I can't simplify that any further and keep whole numbers. So I should add that here. These need to be whole numbers. Whole hashtag? No, whole numbers. So keep that in mind. Like, you could divide 3 and 7 by 3 and get C1H2.5 or whatever, 2.33333, whatever. But you need whole numbers, so you need to make sure these stay as whole numbers. So that's one thing with empirical molecular formula. You might also see problems where, like, the empirical formula for a given compound is C1H2O1. If the molecular weighs, let's say 90 grams, what is the molecular formula? So this is a big one I see year to year to year, where they give you the weights of the molecular formula, they give you the empirical formula, but you need to figure out what is the actual molecular formula. Like, what is it? It's CHO what? C2H4O2? Whatever. So the first thing to keep in mind is these ratios need to stay the same. So if you multiply the C by 2, you have to multiply all of them by 2. So you can do a lot of trial and error until you get a formula that weighs 90 grams and is in the ratio of C1H2O1, so that 1 to 2 to 1 ratio. But that's going to waste time. And you have a lot, but you don't want to waste any of it if you don't have to. So, how do you figure out what the molecular formula is when given a mass and the formula for the empirical? I know that this empirical formula weighs 12 plus 2 plus 16. The empirical formula weighs 30 grams. It's because it's one carbon that weighs 12, 2 hydrogens that weigh 1 each for a total of 2, and 1 oxygen that weighs 16. Well, if I take the molecular formula mass, form mass, and divide it by the empirical form mass, I should get a lovely number. So if I do 90 by 30, that's 3. Oh. Excuse me. So what is that saying? What does that mean? The molecular formula weighs 3 times as much as the empirical formula? How interesting. So let me take C1H2O1 and just multiply those all by 3 to get C3H6O3. So that ratio has remained the same. It's still a 1 to 2 to 1 ratio. Because if I divide them by 3, I get 1 to 1. Does this in fact weigh 90? So these three carbons each weigh 12. That's 36. These 3 hydrogens each weigh 1. That's 6. So that's 42. And these 3 oxygens each weigh 16, which is 48. Add that together. Oh my goodness gracious, you get 90. Woo! Love it. That's about as tough as it'll get with empirical molecular formula. A question that trips kids up. It's an easy question, but it trips you guys up a lot because it can be a little bit, not confusing, but it feels like you need to do work so you don't know like what to do. The question is, what formula is both empirical and molecular? Look at your answer choices. So let's say you had H12O6, H2O, C2H4, and what do I want? What do I want? There's so many formulas. Just make one up. C3H8. That's a bad one. C4H8. What one is both empirical and molecular is the one that you cannot reduce. So if you can reduce it, you don't have an empirical formula, which is therefore wrong. So I can reduce this because I can divide them all by 6. I can divide those all by 2. And I can divide those all by 4. That is a molecular formula for water, which is also an empirical formula because I can't reduce it. That is pretty much it. If I'm forgetting anything, I will do it in the video tomorrow. But I haven't thinking these newer chemistry standards. I haven't seen anything about here's all these percents. What's the empirical formula based on these percents? We've done a bunch of examples in class, but I haven't really seen one. So have a good night, guys and ladies.